This example will be about WiMAX. We are going to demonstrate basic coverage calculations for WiMAX, and then continue to plan a small network for good area coverage. We will perform frequency assignment and link performance analysis, and finally connect clients. This will be a fixed WiMAX example. RAP supports mobile WiMAX as well, but this demonstration is for fixed WiMAX. First, I will create a WiMAX base station at some location where I place the cursor in the map. I right-click, select New Multi-Point Station and Transmitter Position. RAP supports all kinds of fixed wireless access systems, not only WiMAX, but all other standards or systems that are available, and also mobile WiMAX. But again, this will be for fixed WiMAX. I use this template. It is predefined to give a 4-sector WiMAX base. And I will continue to use FDD TDMA, frequency division duplex. I could redefine it to be a TDD TDMA, but we'll stick with the FDD. So there it is in the map, and it also appears as a base station here, and the individual sectors can also be found here in the list view. I will now make a coverage calculation around this base using the coverage tool. And I want to have the calculation for each individual sector, so I use the single station calculation mode. Then we select the appropriate mobile unit. Again, it is a fixed WiMAX case, but for the coverage calculation, we use a virtual mobile that will be moved around the base station to calculate the coverage area. I use a 10-meter high antenna on the base, then on the mobile. We can reduce the calculation area a little, and I make a few settings here of the naming of the result, which will now be taken from the sector name. Pressing OK starts the calculation, and there will be 4 calculations in sequence, 1 for each sector. Now it's ready. The results appear here, coverage results area, and there are default colors set and levels set for the presentation. Minus 82 dBm is the sensitivity of the receivers of this WiMAX system for about 12 megabit per second capacity on the individual link, and the other colors here represent higher signal levels, and it usually is necessary to plan for a higher level than the sensitivity level. So these represent 6 dB higher and 12 dB higher than sensitivity. The results can be shown individually in the map, like that. Let's zoom in around that coverage display, and I will change the map display now to the display which is more clear when I want to display the coverage results only. In this way, it's more evident where the coverage is. It is not obscured by all the map details. Placing the other results on here one by one makes for a pretty busy view. The very irregular appearance of the coverage is due to the terrain features, hills and forests in the area. We make a composite coverage of all 4 sectors by marking them all and hiding the individual ones and showing the composite. So this is the combined coverage of 4 sectors. Red color indicating the sensitivity limit, and green is a 12 dB higher signal than the sensitivity limit. And it's a very typical behavior. WiMAX does not have a very high power budget, meaning that terrain obstructions at 3.5 gigahertz will obstruct coverage quite a lot. I'll change the scale going out again to let's say 1 to 250,000. When I have done this coverage once, I can repeat it very quickly by making a copy of the base using the copy function here and immediate coverage. So when I place one more copy of that base station here, the calculation starts. It will be 4 individual ones, like that, and let's place one up here. And another one, a 4th one down here. In total, there are then 16 sectors in this area. Okay, it is ready, and making a composite of everything here. We'll do that to get a clearer picture of what coverage we actually have. So that's the combined coverage of all 16 sectors. We will now continue to build a larger network, and to do that, it's convenient to use the cost and coverage optimizer. I delete all the existing. I'll delete everything here, and also the results, because we are not going to use it anymore. And there we are. And also I'll delete the base stations, the 4 base stations, because now it will be a complete new planning situation using the cost and coverage optimizer. This tool has many settings, and it is convenient to save the settings of it and retrieve the settings when continuing work or doing similar work in other areas. So for this purpose, I have prepared a settings file, the WiMAX wrap coverage optimizer file, and it sets a few things. I'll change the map scale to include all of the area of interest. And explain what the settings do for us. The indicated area in the map now is our desired coverage area. That polygon has a total area of about 1,900 square kilometers. I can add more areas. I can add points and lines to represent roads if we are going for coverage along roads, but that just complicates the demonstration. So we will go with this simple single area. The type of client is the same that we used for the coverage calculation, so it's a 10-meter high and client, horizontal polarization to match the polarization of the base stations that we are going to place. I have told the program that water is not necessary to cover, so the blue areas are not necessary to cover because we find very few subscribers there. We can introduce population consideration using a population database with population priority. If we do that, we can optimize coverage towards populated areas. I don't do this for this example, so we will have equal priority to all areas except water for this demonstration. Placement here defines characteristics of the base station that we will place, and I use this one, WiMAX Omni horizontal polarization. It has the exact characteristics of a 4-sector base, only that this is an Omni single antenna, which is convenient to use for achieving full area coverage when we do the automatic optimization. And we use a fixed antenna height. I'll say some more about the antenna later. The area is the same. It does not have to be the same. The area within which we are allowed to place the base station. And again, water is omitted from the allowed area. The optimizer supports 3 types of placement of stations. One is existing stations. It is empty here. If we already have a few base stations, they would appear here, and the optimization would consider the existing coverage from them. It would calculate the cost of using the base stations, the existing base stations, and come up with a solution that considers new base stations and old base stations. May very well be that new base stations provide better coverage. It also supports existing sites. We can, for instance, use existing antenna towers as candidates, and that is, as an example, I can search the database. These are existing stations within the area that is drawn in the map, and if I mark them like this, or mark all, they will be considered as candidate sites to place our new base stations. I'll take them away because the example continues with the assumption of having greenfield sites where we build the complete base station from scratch. The cost tab is used to define costs for new base stations. That will be a new tower here, a nominal cost of a 65-meter antenna installation. We have put that to 1 in whatever currency or amount. The coverage optimization and cost optimization can be done for several antenna heights. It will take longer and really not contribute much to the demonstration effect of this exercise. So we stick with 1 antenna height. Cost of building stations can be defined, and cost for distance to road, for instance, if we have to build an access road to the site. The roads are defined in vector themes in the geographical data themes. So if I, for instance, check here to define that consideration shall be taken to these roads, the existence of the roads, I will not do that in this demonstration, but I could do it. Then consideration would be taken from the by calculating the distance to road. This is a per kilometer, by the way, per kilometer unit. Existing sites, existing stations can be defined with their costs also. Okay, now going to the evaluation tab. That's where we define which propagation model to use. I will use the same as I did before, that we usually do. We recommend this one for terrain-dependent propagation calculations. So it will account for forests, for hills, for urban areas, built-up areas that influence the propagation. We plan for some margin. I put 6 dB above receiver sensitivity as the planning margin, and we go for at least 95% coverage. This means that 95% of the area now drawn in the map should be covered with a signal level, received signal level that is 6 dB above receiver sensitivity. Pressing OK starts the calculation. So there we are. It first goes to 25% and then starts placing candidate sites at the location of the circle that moves around in the map. In between each movement, 10 candidate sites are calculated, and the selection of candidate sites is done according to a fairly clever method to achieve a probability of good coverage for each candidate site. So in total, there will be hundreds of potential sites calculated for coverage. And when the progress meter comes to 79%, it goes into another mode, and that is first drawing an initial optimized coverage and then going to fine-tune the coverage. And that is what it's doing right now. It's fine-tuning coverage, and now it is ready. Clicking the result folder for this type of results and opening the result shows that it takes 13 base stations to give slightly over 95% area coverage, 95.2%. I can show the stations in the map viewer with a circle type of presentation as before. But now we are creating this network and continue to work with it. So I generate the stations by pressing this button. Here I have the opportunity to change the configuration of the station, and that is what I want to do. Instead of using the omnidirectional calculation base, I choose one of the station templates that provides sectorization. So we will use these 4-sector WiMAX base stations. They are now created. So in total 13 sectors or 13 base stations, each with 4 sectors. So there are in total 52 bases in the network now. And they are at these locations. Here I could fine-tune the optimization because it's evident that the base stations that are beaming, the sectors that are beaming south, they actually beam out of the desired coverage area. So they logically they really do not contribute to the coverage. So there are a few that I can remove manually, but I won't do that. Instead, we'll just continue with the next part of the demonstration. And that will be a frequency assignment. All these bases are created equal and have the same frequency, and that will not work. They will have to be assigned in a more clever way in order to have low interference and good probability of communication. For that, we use the frequency assignment tool. Starting the tool, the first thing to do is to select the channel plan, and I will select this plan. It looks like this. It's a 12 frequency plan, and it is frequency division duplex with a 100 megahertz duplex separation. So there are 12 pairs of frequencies. We will use that. The next thing is make some settings for the propagation calculations. We'll stay with the default propagation model, the one that we recommend for terrain-dependent calculations. The default mobile, we select the same as we had before, and that was this one, 10 meter high, horizontal polarization. Planning level margin was 6 dB. Maximum server range, reasonable to assume something like 15 kilometer. Actually, we had 20 kilometer in the optimization, so I'll use 20 kilometer here. Now we've done the settings. We will redo this to assign polarization, but in the first run, we will stay with the horizontal polarization. Now, calculating this. It is a terrain-dependent propagation model that accounts for the height data, the hills, mountains. It accounts for the clutter data, forest, urban areas of different types, urban, suburban, dense urban, villages, and so on. And it is a fairly quick, considering the calculation complexity, it is a fairly quick propagation model. RAP has a very comprehensive help function. Pressing F1 starts the help function, and here I can click on the windows and read and see and understand what's going on. Go back and click on something else, read about the allotments. And the blocking settings that are explained here. So assign polarization, for instance, which we will do later, will allow us to optimize both with respect to frequency and polarization. Okay, the calculation is ready. We'll show the sector stations, and they already had the base station and the sectors already had some frequency assignment. Each sector operated on its separate frequency. But here we can see in the margin diagram, margin dB, how much interference we have on each frequency. Frequencies that are shown in blue, they are used by the station that is marked in the upper list. So this frequency has an interference level that results in 11.9 dB of signal to interference ratio, and that is not sufficient. The requirement is something almost 20 dB in order for a frequency to be considered usable for the communication, for the high data rate here, 12 megabit per second. So we have too much interference, and this one is even over 25 dB, too high interference. So we will now optimize the assignment by deleting all frequencies and running the automatic assignment, and this will then hopefully be successful in achieving a good frequency for each of the sectors. One sector could not be assigned the frequency, so we will have a particular look at that. That's WiMAX 0. WiMAX, that is the sector beaming north on base 1. So we will have a look at that. The others were successful. So WiMAX 0 on the one beaming 1, it is at the bottom. At the bottom, we'll go down. It is that one. Okay, here it can be seen that all the colors are red on this, but we can also see that it is only at about 1 dB above the assignable threshold. And we can see here we achieved 19 dB. The requirement for the receivers have been defined to be 20 dB. So if we assign that, it will work quite well. We have only 1 dB of interference, so that's not a big deal. Assignment now can be manual, so double clicking here assigns that frequency. We can also see from this that this network actually made use of all frequencies, because there is some interference contribution on all frequencies. We will now redo the assignment and with consideration to polarization, and see what we can do. And I need to recalculate for this, because now it calculates both vertical and horizontal polarization, and there is about 20 dB polarization discrimination defined for the antennas. This means that an antenna transmitting vertical polarization its interfering signal will be attenuated by almost 20 dB when receiving with an antenna of the opposite polarization. Again, this is a fixed WiMAX case, and it is quite reasonable to use polarization optimization for fixed WiMAX. It is not so for mobile WiMAX, because there is no really good control over the polarization in the mobile situation. Okay, it's ready. Now I reassign everything, so we delete all frequencies again and assign. And we will see how the result will be now and what number of frequencies this network will require. It needed 12 frequencies before without using polarization assignment. And we should expect some reduction in that. I should also say that this is really a worst case assignment situation. The mobiles are placed at the worst locations from an interference point of view, and in reality they may very well not be there. Okay, we got no information message of non-assignability, and we can see now that the network actually can be assigned 1, 2, 3, 4, 5, 6 frequencies. So instead of using 12 frequencies that were required when everything was horizontal, we now can do with just 6 frequencies. The indication here is red. This means that frequency needs to be changed in polarization from horizontal to vertical. This one stays as it is, horizontal. Okay. Would you like to save your assignment? Yes, I wish to do that, and let's see what happens. Okay, we get these messages. Should we change the polarization? No, I can do that, but I will not do it. It's obvious how to do it. You change the antennas to vertical polarization, and it goes through. So we will not do that. And okay, there we are. Because for the continued exercise now, we will run it as it was before with the network. Now, continuing to place clients in this network, what we have done so far is optimize coverage, assuming coverage should be over all the map area displayed here. Let's now place clients. Clients can be imported using the station list import function here, import station list. And that may be the case if we have hundreds of clients in an Excel sheet with the coordinates. It's a very quick operation to import them and subsequently connect them to the best serving base. We will do this manually instead. So at some location here, I place a new station, and this will then be a client. WiMAX, where do I have the WiMAX here? WiMAX client HP, horizontal polarization, or actually I'll use this one, 10 meter horizontal polarization, because that is the exact one that we've been using before. So this is CPE1. And it has a nominal frequency. This will be changed when we connect with the automatic linking to the bases, and it has the fully defined technical characteristics. The antenna, for instance, has a pattern that looks like this. It is narrow in the horizontal plane, and it is also narrow in the vertical plane, because this is a client assumed to beam just straight to the base. So there it is. Now I will quickly create a few more of them. When I'm ready with that, we will use the automatic linking feature to link them to the best serving sector. That is by pressing the control key and then moving like this. So I will do this quickly to just place clients here and there, and let's have a few over here. The real planning situation when doing this in a live network or a network to be implemented in the early planning stages is probably to have client lists in a database or an Excel sheet and import directly from there. Okay, there we have quite a few of the clients, and they appear here in the list. So what I do now is I mark all of the new clients, right click, use the link function, link to sector, and here they are, the bases, and each base has its 4 sectors. We will use a best server calculation to have an automatic identification of which sector is giving the best service to each client. Press OK. Here, settings of propagation model and so on. Maximum server range can be used. This is useful if there are hundreds of or thousands of clients. Then it would be quicker if we limit the server range. Now I don't need to do it, so I won't do it. Here we can put in some margin. Let's put in the 6 dB margin that we have used so far for this exercise. Pressing OK links everything, and there was no message of unsuccessful linking, so this means that all clients can be linked to at least one sector, and now they are linked to the best sector in each case. I'll hide the labels now because it's a bit busy map. The colors here represent the frequencies used for transmit and receive. So the clients are always transmitting on the low frequency because we have defined it to be like that. Bases transmit on the high frequency. When I double click on a line here, the terrain profile between client and sector is displayed with the first Fresnel zone, and that is to be able to make a quick check of the feasibility of that it's really able to communicate. Okay. Here I got a crash. So no, it wasn't a crash. It was just so we will continue. It wasn't a crash. It was just some situation, my computer doing something else on the network, because this is a quick, as you can see, it is a quick operation. Oh, it's doing something else for me now. Okay, this will have to be edited out of this demonstration. There we are again. Okay, now I have accidentally clicked on this measure icon. Unclick that. That is a dynamic profile. So what I've been doing is, in some cases, in not showing the real link, I have showed a potential link. There we have two. Oh, it is doing something strange here. Okay, we can also check the links now for performance. They are all linked here. You can use the radio link performance tool to calculate performance. Here we have, for instance, on that one, we have 22 dB flat fading margin. Which is good. And so on. Each of them should be okay because we have defined all the sensitivities accordingly and required 6 dB above sensitivity as the required signal strength. So all of them are okay, and the automatic linking worked the way it should. There are other useful functions in RAP to support the planning. For instance, let's say that we want to calculate the required antenna height for a client to be able to connect to a particular base. I will demonstrate that, and I will clean up the map a little. So we remove the area. We'll remove all stations. Remove all links. Remove all stations. There we are, and finally remove profile. Okay, so let's assume that we have at this location, I'll show it in the map, that's WiMAX base 1, and we want to calculate the required antenna height for clients in that area to connect to the base. That is done like this. Select required antenna height. We can define the clearance, and WiMAX can tolerate some obstruction of the first Fresnel zone. Let's assume that this is a good planning criterion. It goes for the straight the line of sight, and that is for a curved Earth with effective Earth radius 1.33 that we have here. And we should do this in a high resolution and use best terrain resolution in order to make use of the available accuracy of the terrain database. Press OK. The calculation is performed. And now it takes a little longer than before because I use, as I said, maximum terrain resolution, but it's a quick and useful calculation anyway. And there we have the result. So, here it shows that within the 30-kilometer radius that I calculated, if we wish to have coverage, line of sight coverage to every point within that circle, we have to use a 152-meter high antenna, which of course is not realistic. So let's put in a few antennas here. What can we do with 5-meter, 15-meter, 25-meter high antennas? So this is the area of visibility to that base. The base has 65-meter high antenna. Within the The green areas, it's only required a 5-meter high antenna. The yellow areas, we require 15-meter high, and red, we require 25-meter high antenna. At a particular location, we can see the exact value. So here we need 24 meters. Here we need actually 0 meters because that's probably a high mountain, and 5 meters there. So this is a very useful calculation that a commercial operator may like to make available on his website for each base station or network, because this can be done for all base stations, and use another function, multiple calculation, and then show maximum required antenna height, it's called, and then it shows in every point, it shows how high antenna a client is required to connect to just one base. Okay, that completes the WiMAX presentation.